Alright, welcome back to another video on math and beats. Today, I'm going to do a video on introducing how to graph relations and functions. So, to begin with, we're just going to refresh our memory. What's a relation? What's a function? Remember that a relation is any set of ordered pairs, and a function is a particular type of relation for which every input has exactly one output. We've looked at the symbolic representation of functions so far. We write y equals f of x. That's our symbolic representation of a function in which you produce ordered pairs from this type of symbolic notation, which look like x comma y's, or if you prefer, x comma f of x's. The x is our input, and our y, also known as f of x here, that's our output. So function, we need a collection of these ordered pairs such that every input has exactly one output. That's where we're at. We'd like to now look at a visual way of representing such an idea, and that is through the concept of graphing. So we're going to introduce how to graph these types of functions. And to do that, what we do is we take two real number lines and we intersect them at a right angle, as so. So here is a vertical line. That's going to end up being our outputs. And here is a horizontal line. Those are going to represent our input values. This diagram right here is what's called the Cartesian plane, after the philosopher and mathematician Rene Descartes, who was one of the first to kind of come up with this idea. This is the Cartesian plane, and we plot ordered pairs in this plane. How to do so? Well, we set up a coordinate system such that we measure where these points are in the plane relative to some location. And that location is this spot where these two axes intersect. That point right there is the point 0, 0, which we call the origin. And all of the other ordered pairs that we measure are relative to this spot. Okay, so how do we graph such an ordered pair? Let's just pretend we're going to graph some ordered pair up here. Let's call that point some x comma y, whatever it may be. So to get to that point, starting from the origin 0, 0, we first move left or right accordingly from there, depending on where our point is. Here it's up there at the top right. So we're going to move right x units, and then from there we move up y units, producing the ordered pair x comma y. So that's how we plot points. Depending on what x and y are, we could be at different locations in the plane. We assume that when we move to the right, that is the positive direction. So this is the positive direction for at least the inputs, and then upwards for the outputs, that's also our positive direction. That also means if we move to the left, that would be the negative direction, and if we move downwards for outputs, that would also be the negative direction. So we're going to practice plotting some of these here in a moment, but before we do, we want to also introduce some vocabulary. Depending on where we are in the plane, x and y can have different values, and depending on those values also tells us correspondingly where we are in this Cartesian plane. So a couple of things. First, that horizontal axis, the one we labeled with x, that is what we call the x-axis, or in general we would refer to that as the horizontal axis. Always down here are inputs, always. So we always put the inputs down on the horizontal axis. Likewise, the vertical axis is called the y-axis, and that's where we put our outputs. So those are two specific locations where a point can be, as we'll see in the upcoming example. But what if you're not on the axis? Then you're in one of these four different locations where the axes split up the plane into what we call quadrants. So starting at the top right, if you're anywhere up in this location, that is what we call Q1. Now this Q1 off on the side stands for quadrant 1. It's just a way of keeping track of things. And then obviously there's 3 more quadrants, so how do we measure? We measure counterclockwise. So over here at the top left, that is your quadrant 2. Keep going counterclockwise to the bottom left, that is your quadrant 3. And then finally at the bottom right, that is quadrant 4. So there's really 6 different places that a point can be located in the Cartesian plane, either in one of the 4 quadrants or on one of the axes. So that's about it for introducing the Cartesian plane. How to plot points: move left or right x units from the origin, and then from there move up or down y units from that location. And of course, that all depends on whether x and y are positive or negative, or 0 perhaps, as we'll see. So we should look at an example here. Let's do that. So down below here we have an example. We're just going to practice plotting some of these ordered pairs. And we see that in this example, we just want to plot each of the ordered pairs that are given to us, and then also state which quadrant or axis it belongs to. So we're going to start with this first point, this first ordered pair, 1, 2, and that means from the origin, so here we are at the origin right there, we move to the right 1 unit, since that's our input value and it's positive, and then from there we move up 2 units, so that point right there is the point 1, 2. And there you have it. So where is this point located? As we just described in the previous explanation, this is in quadrant 1. All right, let's keep going. Part B, we have the point -1, 1, again starting from the origin. Now our input is negative, so we're going to move to the left to -1 horizontally, and then from there we move up 1 unit output-wise to the point -1, 1. This point is in quadrant 2. Now you don't have to draw these arrows every time you plot a point, but since I'm trying to introduce the idea, I'm doing it for you. You also don't have to necessarily label these points, but we're doing it again because we're trying to reinforce the idea. All right, let's keep going. Part C, 1, -2. That means move to the right, +1 unit. And now the output is -2, so we're going to move down 2 units to this point right there, which is the point 1, -2. Down at the bottom right, this is quadrant 4. Keep going. Part D, -2, -1. That means we're going to move left from the origin 2 units to -2. And then the output is -1, so move down to -1. So here's the point, -2, -1. That is located in quadrant 3. All right. A couple more here. E and F both have one of the coordinates being 0. In the first one, 0, -1, we're not going to move left nor right from the origins because the input is 0. So we just go straight down to -1, and here we are. There's the point, which is 0, -1, and that is on the y-axis. So in fact, if your x-coordinate is 0, your input is 0, you will always be on the y-axis, or the origin if y value is also 0. Finally, part F, we're going to plot the point 2, 0. So That means we move 2 units to the right from the origin, but then we do not move up or down since the output, the y value, is 0. So that point right here, 2 comma 0, is located on the x-axis. So there you go. There's 6 different points, one from each of the locations that you could actually plot in the Cartesian plane. And hopefully that gives you a decent idea of how to plot such ordered pairs on the plane. Now, when we graph an entire function, it all depends on what ordered pairs we have in the function, but when you plot all of the ordered pairs for a function, the result is what we call the graph of a function. We'll look a lot more at all the graphical ideas moving forward, but right now we're just trying to introduce the idea. It ends up graphing is a giant part of mathematics. It helps us visualize how functions behave. Also, notice that in this example that we just looked at, I put some grid lines, as I say, through some input and output values. So all those different vertical and horizontal lines that you see in this plane that are not part of the axes, that's not always necessary to draw, but I did it for this particular example because it forms, as what we say, a rectangular grid, a bunch of different rectangles when you intersect input and output values depicted through lines. And for this reason, when we plot ordered pairs in this setting, we often refer to the coordinate system as a rectangular coordinate system. So most of the early mathematics that we'll look at will live in this coordinate system, but it ends up there are other various coordinate systems as well that at some point we'll make some videos on that. All right, so let's keep going. We're going to make up an example now, and this is going to help us figure out the difference between when we look at graphs of relations and functions, whether we have a function or not. So we can graph functions, we can graph relations, any collection of ordered pairs we can graph. So this is what we're going to do in the next example. Another example here. Let's consider the relation. We'll just make something up. How about we consider the relation, the set of ordered pairs, 2 comma 1, and then maybe 4 comma 3, and then 2 comma 5. So nothing too exciting, but it is a collection of ordered pairs. Question A. Is this relation a function? So this is kind of a review question, but it's going to help us exemplify an idea. And so we should know how to answer this. We see that there are 2 different ordered pairs with the input of 2, and those 2 different ordered pairs actually have different outputs. So for the input of 2, we have 2 different output values. That violates the definition of a function. So this relation is not a function. So the answer to this is no, it is not a function, as the input of 2 has 2, and here's the important word, different outputs. So not a function, it's still a collection of ordered pairs which we can plot, and in fact that's what we're going to do. Let's plot the relation. Sometimes we use the word plot to synonymously with the word graph. So we're going to graph or plot this relation in the Cartesian plane. All right, so here we're just going to draw a plane. Nice vertical axis. We'll label that y, assuming the outputs are y's and the inputs x's, the horizontal axis. And we should set up some tick marks here to keep track of what's what. Notice that all my inputs and outputs here are positive, so all these points are going to live in quadrant 1. I'll just go ahead and label some horizontal tick marks, 1, 2, 3, 4, 5, and then we'll draw some vertical tick marks, 1, 2, 3, 4, 5, trying to be as neat as possible. Okay, so let's plot them. 2 comma 1, it's about right there. And then 4 comma 3, just eyeballing it, it's about right there. And finally 2 comma 5 is right there. So that's the whole collection of ordered pairs here. We already know it's not a function. And the reason it's not a function, remember, was because the input of 2 had 2 different outputs being 1 and 5. So those points are depicted right there in this graph. And so you say, okay, we know it's not a function already. We see that. Now graphically, notice in this example, we can actually draw a vertical line through these 2 points, and that vertical line will intersect both of the points. And that's because they are 2 different vertical locations, 2 different output locations for the same horizontal or input location. That line is not part of the graph, but I'm just trying to show you that under this circumstance, that is something that is going to happen. And in fact, we can think of, hey, look, if we have any situation of a relation which has 2 different outputs or more for one single input, then you're going to have this. That is, you're going to have the situation in which you can draw a vertical line through more than one point in the graph. Hence, you have more than one output location for the same horizontal location. This produces a test for graphing, or excuse me, for determining whether a graph of a relation is a function or not, and that is called the vertical line test. So this is a test for figuring out whether or not the graph of relation is a function. So it says, given the graph of any relation, if there exists at least one, so one or more vertical line for which drawn through the graph passes through more than one point, then the relation is not a function. Just like in our example above. If we draw a vertical line and it passes through more than one point in the graph of the function, then what that's going to mean is that there are multiple outputs for a single input, hence violating the definition of a function. Whereas if that never happens, otherwise, then it's a function. So a function graphically means no matter what vertical line you draw, it passes through at most one point on the graph of a function. So let's do one last example just to get this idea across. We're going to draw a little Cartesian plane here, and I'm just going to graph a few points. 1 point, 2 point, 3 points. There's some points. I don't even know what they are. It doesn't matter here. So you say, okay, that's my entire graph. If I draw a vertical line through every ordered pair, just pretend it goes there, on the graph, then we have that each of these vertical lines is only passing through at most one point. So by the vertical line test, it is a function. We would say that this graph is that of a function as it passes the vertical line test. So it's a nice graphical way of figuring out whether your relation is a function or not. If it did something like above in this example, we would say that it failed the vertical line test, so it's not a function. So it's as easy as that given the graph. Your explanation for whether or not it's a function can now be based on the vertical line test. And that's your little intro on graphing sets of ordered pairs. We're going to get way more gangster with this as we go along, but for now that's your introduction. So just to refresh what we did, we talked about the Cartesian plane. This is the place where we plot ordered pairs in general, both for relations and functions. Any point that we graph, x comma y, is always plotted by first moving left to right x or input units away from the origin. And then from there we move up or down accordingly. The vertical amount of units, the output units, and of course, those locations all depend on if x or y are positive, negative, or 0. We have that this plane is produced by intersecting a horizontal and vertical real number line, the x and y axes, accordingly, and then this chops it up into 4 other pieces called the 4 quadrants. Quadrant 1 starting at the top right, moving counterclockwise around to get your other quadrants. We plotted some points here in this example, and then we looked at a situation which showed how the vertical line test would work, and we stated the vertical line test, right? Any vertical line drawn through a function should pass through the graph at most one time. If it passes through any point more than once, any vertical line, then you do not have a function. So that's about it. Stay tuned for more videos. This is Math and Beats. Subscribe, like the channel, and now it's time for some beats. All right, later.